type of regression that we're going to learn in this course. And the final one is the exponential model. Okay, so we talked about the linear, we talked about the quadratic. Now we're going to look at how can we perform the exponential models. So exponential models represents quantities that change at a constant percent rate. Okay? So what did we learn about linear? How can I tell that something is linear? First degree, first difference is constant, you mean? Yeah, first difference is constant.
Straight line.
It's a straight line. How about the degree of the equation? Degrees, right? So the thing is that when linear, your first difference is constant, right? So when you do y2 minus y1, you get a constant answer, okay? When it comes to exponential, your first ratio is constant, okay? So the ratio means what's a ratio? What does the word ratio represent mean? Addition, subtraction, division, right? So ratio means division, okay? So when we do the table of value, when I divide y2 by y1, I get a constant answer. And this is how I know that this is an exponential function, okay? In a table of values, we call that the growth and decay factors are equal. The graph resembles an exponential curve. And remember, an exponential curve has a flat end and either a fast increasing end, or it has a decrease and then a flat end. So this one represents an exponential curve. The equation is written in the form of y equals a b to the power of x, where a is your initial value and b is the growth or decay factor. Notice that the exponent is the x, which is the variable, okay? So a and b, they're going to be numbers. X is your variable. X is your letter. The exponent is your variable. So in an exponential equation, y equals a b to the power of x, the growth or decay factor is given by the value of b. Now, if b is greater than 1, the relation is growth. And remember, we talked about that before, and we said that if you have a rate means a percent. If you have a rate and you know it's going to be growth, so it's an increase, it's going to be a 1 plus I to the power of x, where the 1 plus I becomes your b, right? If you know your rate, let's say your rate is 20%, then that's what's going to go in the I. Do you guys remember that?
Yeah.
Okay. Now, the 1 plus I become your b. That's what makes your b. So, look at your terminology. Growth factor is b. So b is your growth factor, and the growth factor is equal to 1 plus the growth rate. What's the growth rate? What letter is it represented by?
The I.
I. Okay, so b is equal to 1 plus I. You need to know this terminology. You need to know that the growth factor is b, the growth rate is I. That's a percentage, yeah. But then you have to change it to this. So if I want to find the growth rate, so if I give you, let's say that you have an equation that looks like this, y equals 3, 1.2 to the power of x. What's 1.2? What do we call 1.2? Growth factor. How can I find the growth rate?
Equal 1 plus I.
So your growth factor, I don't understand what you guys are saying because you're all talking in your, I don't know. So your growth rate is b, so that's 1.2 equals to 1 plus I. Right? If I'm solving for I, all what I have to do is subtract 1. So that's going to be 1.2 minus 1 equals to I. So you see that the growth factor, which is b, minus 1, that gives you your growth rate. That's what the formulas say. Are we okay with that? Now, if your base is between 0 and 1, then the relation is dk. And remember that with the equation we said y equals a 1 minus I, right? And that what represents a decay factor, or my decay exponential decay, right? And 1 minus I is what makes your b, right? So once you plug in your rate, that's what's going to make your b. So the decay factor b is equal to 1 minus the decay rate. So if I have something that looks like this, y equals, give me an example, with a decay. 1 equals what? 5. So give me a number that's between 0 and 1. Okay? Okay, let's say I have this. What's your b? So b is 0.8. And b is made of 1 plus 1 minus I, right? So b is 1 minus I. And how do I know it's 1 minus I? Because it's between 0 and 1. Okay? Because it's between 0 and 1, it's a decay, that means it's a 1 minus. How do we find I?
Isolate the I.
Isolate for I, so what do I do?
Switch the I and the 0.8.
That's right. So if I bring the minus I to this side, it becomes a plus I. Bring the 0.8 here, that becomes a plus 0.8, minus 0.8. So it's going to be 1 minus 0.8 equals to I. Right? So that gives me an I of 0.2. Okay? Which is 20%. Does that make sense to you guys? So if you know the B, if you know the growth factor or the decay factor, you can use either 1 minus I or 1 plus I to find your growth or decay rate. All right, so in a table of value, in order for me to be able to identify if it's exponential or not, I have to do the first ratio, which means I have to do y2 divided by y1. So y2 divided by 1, y1. So that's going to give me 0.71. 15 divided by 25, 0.6. And 5 divided by 15, so if you look at that ratio, is it constant? No. So is it exponential? No. So I know this is not exponential because the first ratio is not constant. The second example, again, if you look at the x values are going up by 1. So you want to have that consistency, okay? You want to make sure that all your numbers are going up, all the x values are going up by the same amount. Which I won't be tricking you at all. Like, I won't be giving you something that's not like that. All right, to find the ratio here, so we have to do y2 divided by y1. And then I can divide 64 by 51.2, 1.25. 80 divided by 64, 1.25, and 100 divided by 80 is 1.2. Okay? So in this case, you realize that the ratio is exactly the same, it's constant. Sometimes when we're finding ratios, and especially with graphs that where we're collecting data, you're going to see the ratio is not 100% constant. You're going to see, like, let's say 1.25, 1.24, 1.2356, you know, like something close. As long as you can round up to something that's similar with the ratio, then that's fine. Okay? So sometimes the ratio is going to end up being, let's say, don't write this, but sometimes it will be like 1.25. 1.235, right? 1.26, 1.24, right? So you see that this is close enough, right? Especially if these numbers are collected, okay? They're close enough for you to realize that it is actually exponential, okay? So in this case, I know it's exponential because so in the table of value, I'm looking at y2 divided by y. Let's look in the graph. Is the first graph exponential? No. So not exponential, this is a straight line. And the second one, what can you tell me about it?
Which one do you write?
Yeah, D.
Yeah, it's exponential.
Yep. So it is exponential. You see kind of a slow growth at the beginning and then a fast growth after that. Okay? So we see a slow increase and then a fast increase. And that's what describes an exponential curve. Okay? So this resembles an exponential curve. We have a slow increase at first. Followed by a fast increase. Out of the two equations, E and F, which one do you think is an exponential
The E.
equation?
The E.
E. Why do you think it is?
Because we have the exponent is
The exponent is the variable, that's right. Okay, so you see that because your exponent is a variable, it's an exponential. How about the second equation? What is that? Quadratic. It has a degree 2. So here's what I want you to do for the next two equations. So for example 2, you're going to have to determine the growth or decay rate. Okay? And then for this one, you're going to use Desmos to graph these two equations. And then you can sketch it. Okay, you can sketch it here if you want, but use technology to graph. And then you're going to compare these two. Tell me what's similar, what's different between these two equations. Okay? So use graphic technology to graph, compare the two. Describe what do you see the same, what's different. And then you're going to change the colony A. You're going to change the initial to 200 and then compare the one with 200 and the one with 100. Okay? You understand what you guys have to do? How would the graph of colony A change if there were 200 bacteria initially? So you're going to compare, the equation would become y equals 200 2 to the power of t, right? So you're going to compare that equation to that equation in this question. Okay? Start with the first question though and answer